So first is nomenclature, which is really boring, but we'll just get it out of the way. So you guys know how to name aldehydes and ketones? You just need to know the suffix. So a suffix for aldehydes is Al, and then for ketones, it's ONE. So the first one, and like you know how to do IUPAC, like find parent chain, find substituents. So the first one, you find the parent chain and then the substituents. So it's 1, 2, 3, 4, 5. It's a pentane. And then there's a 3-methyl on it. So it's going to be 3-methyl pentanol.
Pentanol?
Yeah. The second one, yeah, it is acetone, but what's the technical name? It's propanone. Then you don't have to specify the number because there's only one place a ketone could go. Then for a third one, you could call it a few things like methyl phenyl ketone, or like benzyl ketone, whatever. But the common name is acetophenone. Yeah, everyone calls it the uncommon name, like methyl phenyl ketone. And then, well, this one over here, it also has a common name, acetaldehyde. Also called ethanol, because it's a 2-carbon chain and there's an aldehyde at the end of it. This one?
Yeah.
What'd you say?
5 and 5 and 7. 1, 2, 3, 4, 4 and 5 and 7.
Yeah. 4-ethyl hexanone.
Isn't the longest chain going towards the top?
You're right. And the last one, 2-methyl. Yeah, exactly. All right, so there's a few nomenclature ones in the test bank, but they're like easy 3 points basically. So moving on to making aldehydes. So from a primary alcohol, you can go to an aldehyde with a couple of methods. So which methods could you use to oxidize it? Wolff-Kishner gets rid of ketones. So it's just PCC and Swern. PCC, the reagents are PCC over CH2Cl2. And then for Swern, DMSO COCl2 over NET3.
Four agents,
Um,
one of them.
yeah, all of them can alcohol to aldehyde. Well, same thing for ketone too.
One difference between BCC and BCC in percent of the glycol.
The difference between, oh, it's just like the name of the oxidation. So like PCC oxidation uses these reagents. That's all.
Swears with the.
Mhm.
So, is that CCO?
Sorry,
Just wanted to make sure.
it's COCl2.
What's on the bottom there?
On the right side,
Yeah, just one.
NET3. So triethylamine. And then to bring it back, we can use two reducing agents, the lithium aluminum hydride and the sodium borohydride. Okay, so that's only for if you're going to, or from an alcohol to an aldehyde, but you can go from a bunch of other stuff to an aldehyde. So if you're taking an acyl chloride, so remember, this is your acyl group, and then if it's a halogen attached to it, becomes an acyl chloride. So if we're going from that to an aldehyde, do you remember a reagent we'd use? No, it was in his last lecture, something new.
Aluminum H.
Yeah. Yeah. So it's gonna be lithium aluminum hydride, OTBU3. And then it has to be cold. So on the bottom, it'll be like -78°C.
So it has, so anytime you see a seal with a halogen, in order for it to go back to an aldehyde, it has to be cold.
Yeah, you have to use this reagent over cold temperatures.
Okay.
And then for an ester to go back, we use something called, I don't know how to pronounce it, like dibol? Okay. So we use dibol H, also cold. And then this is an ester. Yeah, it's the same thing. And then for the cyanide or the nitrile, it's also the exact same thing. Except you can use different temperatures with it, which is not important, but. Okay, and these are just the structures of the reducing agents. Not important to know, but it's in there. But dibol can do something else to esters. Well, if you have a cyclic ester, a lactone, it's going to oxidize into an aldehyde, but then you break open the ester and you get an aldehyde and a carboxylic acid. So if you react a lactone with diol, you get this. Okay, and then to turn secondary alcohols into ketones, it's the exact same thing as aldehydes. So to oxidize it, you use Swern and PCC. And then to reduce it, you use the same two reagents.
When did you do the KMNO4?
KMNO4, the only time I saw it for this chapter,
Was it secondary alcohol or something?
you can use it to oxidize. Oh, what do you use to oxidize?
That basically like primary or something? I don't know, secondary.
I think KMNO4 would just take it all the way to like a carboxylic acid. I don't remember either. But also for this chapter, KMNO4 does something important. I saw it on your test. So if you have a benzylic, carbon, just like a methyl sticking out of a benzene, if you react it with KMNO4, it's going to turn that methyl into a carboxylic acid. Yeah, just for this like specific type of methyl. It has to be attached to an aromatic ring. And I forgot to put this on the handout, so.
But the other reagent like BCC or Swern ends with the same.
It's
For-
just KMNO4.
No, I know. But if we use the Swern or BCC with side,
Oh, on a seed of,
No, let me take that.
Is
Is that okay?
It's gonna be a
Can you
ketone
go
or
more?
like the product will be ketone or aldehyde,
Is that using? The KMNO4 on the benzene, whatever,
Mhm.
if you use
the
PCC or Swern.
no,
What's
it's
it gonna make?
nothing. Like if you have an alcohol coming out of the benzene, then it would, it would turn it
BCC or Swern with it.
aldehyde, aldehyde.
Then aldehyde.
Yeah. I think actually to make a benzaldehyde, you would need to start with this. Like a benzylic alcohol. Yeah, not like a phenol. Okay, and then there's one more way we can get ketones. So if we do a Grignard on a nitrile group, it just turns into a ketone. So you know how Grignards work, you just stick them onto the carbonyl, in this case, like one end of the triple bond, and you get this intermediate. So you've just added the R group of the Grignard onto the, or to the same carbon as the R group from the nitrile. And then this intermediate is called your imine. And then after you react that with water, you get a ketone. Okay, cool. So now we've made aldehydes and ketones, and now we're gonna add stuff to them. So this is the basic idea of any nucleophilic addition onto a carbonyl. You just have your carbonyl, you have a nucleophile, and the nucleophile gets added and turns it into an alcohol. And you can make the nucleophile more reactive using an acid or base. So an acid catalyst, well, it doesn't do anything to the nucleophile. The acid catalyst just attaches to the carbonyl and makes that much more electrophilic. So acid catalyst makes the electrophile more electrophilic. And then you could also use a base catalyst to deprotonate the nucleophile. And in that case, it would make the nucleophile more nucleophilic. And I saw word problems on this. Yeah, but it's straightforward, just memorize it. It was literally the same wording as this. It was like an acid catalyst blank does blank. Okay, so now here is where I started getting confused when I took the class, because everything is like similar and there's like 5 gazillion things to memorize. But when you do nucleophilic additions, you can get like all 5 of these as common products and you get quizzed on the name. So you can have an acetal or a ketal, and then you can also have a hemiacetal and a hemiketal. So first, to identify if it's an acetal or a ketal, you look at the stuff attached to the oxygens. So we're looking at this carbon. To identify if it's an acetal or ketal, you look at the R groups attached to it and ignore the oxygens. So if the R groups are both like carbons, it's going to be a ketal. If you have like this, where you have 1 R group and 1 hydrogen, it's an acetal, because it's a derivative of a ketone and an aldehyde, respectively. So after that, we look if it's hemi or just normal. So hemi means something like this. So here, this molecule is what? Acetal or ketal? It's acetal. And then on top, we have 2 different things. So we have an OR and an OH. So because we have 1 alcohol and 1 ester, it's a hemiacetal, because it's like half alcohol, half ester.
Is hemi different?
It's hemi. And then if we look left of it, we see that these 2 groups are both OR. So they're both OR, it's just going to be an acetal.
So the last one is hemi because it's half
Half
alcohol and half ketone,
ester,
ester.
but it's half OH, half OR.
Okay. And the one next to it is just acetal.
Mhm. Because it's 2 ORs. So then what about this one to the left over here? It's a ketal, because there's 2 R's and the 2 oxygens on top are esters. And then what about the very first one? Hemiketal. And then the second one is a geminal diol. Remember, geminal means coming from the same carbon, and diol because there's 2 alcohols. So you can call it a geminal diol or a hydrate.
It's not a ketal or acetal.
Nope. but you get it through the same reaction that you get ketols and acetals from. Sorry.
You're okay. So the honey ketone is half OR, half OH.
Mhm.
And it's a ketone because the bottom six ratios are R.
And then the top is both OR as well. If this thing on top is both OR, then there's no
I'm talking
hemi.
about the first
Oh, yeah,
one. Okay. Okay.
cool. So that's what they're called, but now
So where is that acetate?
just acetal is on the bottom, you have an R and an H, and on top you have two ORs. That's it. Okay, so the reactions to make these are simple. I think all of these reactions with like acetal, ketal, whatever, and also in the next section with the amines, they're all completely reversible. So technically they should be drawn with the double arrows, but I think that's annoying. So most people just skip that. But just be aware that they are reversible in equilibrium. So to go from an aldehyde to acetal, you give an aldehyde and alcohol. So just like this.
What's reversible?
All of these reactions. So to go from an aldehyde to a full acetal, you need two reactions. You reacted with alcohol twice. So the step in between is going to be a hemiacetal. So this first reaction with an alcohol gives you a hemiacetal.
What's that part of OH? Is that just the region?
This is any alcohol.
Any-
Yeah. And then you react it with alcohol one more time, and then you get a full acetal.
So they react with the alcohol twice.
Now, if there was only said one, like, one, what do you call it?
One equivalent.
Yeah, one equivalent, it would just stop with the hemiacetal.
I think so. I don't know how that's going to work actually. I think just it's multiple choice, so use your best judgment. Yeah.
For our acetal or acetate, it is like inside or beside or.
Oh, it's whatever is
Different than any difference or still.
Is it changing the name of the maybe or?
Like this is methyl CH3 CH2 and C2 so is it still methyl acetal or beside that or?
Oh, I don't think it's like a part of naming, or I've never seen it as part of naming. It's just like a way to describe that group. I think they might just be named as like ethers or alcohols in the final product. Okay, and then to go from a ketone to a ketal, it's the exact same thing, except the bottom is not RH, it's RR. Exactly the same. Start with the ketone, give it an alcohol, and then you get a hemiketal. And then on the bottom of these, you'll usually see like an acid catalyst, but it doesn't do anything. It's just there as a catalyst. The real like reactive portion is the alcohol that we care about.
This isn't too bad.
Yeah, it's fine. Okay, and then there's one more reaction for these. You can make cyclic acetals if you use a diol. So if you use a normal alcohol with one OH, you get a hemiketal, whatever. But if you use a diol like this, you end up attacking from both sides and get a cyclic version. So let's say we start with a ketone. Oh, I said acetal. It doesn't matter. You can start with a ketone or an aldehyde. Then we give it this diol. And then you react it with an acid catalyst, and you get this interesting looking thing. It's still two ORs on top, except the R groups are now connected to each other.
That HA.
The acid catalyst.
Would you do that with, is there such a thing as a?
Yeah, we do with either one. And then this is also on the worksheet because I forgot to put it in there. But if you want to make a geminal diol, you do all of this, but instead of alcohol, you use water. So you start with ketone or aldehyde. You give it water, and then you get a geminal diol. Okay, can I move on? So now I have amines. Same idea. You have a bunch of molecules that are really similar. They have interesting names, and then we do reactions to make them. So the very first thing, if you remember from like some reaction intermediate we did a while ago, it's called an imine. So you have like 3 R groups attached to this nitrogen, and then it's double bonded to like the carbonyl carbon.
If one of these are hydrogen amine with A,
No, if the N is a hydrogen,
yeah.
it's still an imine.
Imine.
Mhm.
What is amine?
Amine is like an NH.
That's-
This, like, if that NH is arranged in like this structure, you call it an imine. I think it still counts as an amine though, because it's the nitrogen. The second one is called an enamine. So this is when the double bond is not directly attached to the nitrogen, it's on one of the side carbons. And you can see that the double bond is on the more substituted side. So whenever you're forming enamines, you're going to put the double bond where it's going to be the most stable. This third one is called a hydrazine. Just two amines connected to each other. The fourth one is a hydrazone. And then the very last one is an oxime. That one's kind of easy because it starts with an O and then there is an alcohol attached to it.
So in the like rules for naming this amount,
I don't think so.
common,
Like for IUPAC,
yeah, like,
if there are, I don't know them.
yeah, well, this is a common name, should be more right.
It's just like the name of the functional group, really.
Uh-huh.
Yeah, I never learned the IUPAC rules for these. Okay, but to form them, to form an imine, you take an aldehyde or ketone and give it a primary amine. Like for all these, you just memorize like starting thing, what you reacted with, and then what functional group it gives you in the end. And these are really simple because basically all you do is chop off the H2 and chop off the oxygen of the carbonyl and then like cut and paste this NR group onto it. So you see, we literally just like glued it from the amine onto the carbonyl. And then you get an imine.
With an A and an
And I.
I.
Oh, it's describing the reagent because the NH2R is primary. So carbonyl plus primary amine gives you an imine. And then you can think like the I in imine stands for primary. For enamines, it's the same thing, except you use a secondary amine. I'm gonna draw it like this.
It can be either ketone or an aldehyde, it doesn't matter.
Yeah. So over here, I drew a ketone, and then it has a propyl on one side and a methyl on the other side. So in the final product, which side is the double bond going to go on? So remember, we are just cutting and pasting the amine onto the carbonyl. And we don't put the double bond onto the nitrogen. We put it on a carbon away from it. So we could put the double bond either on this side or this side down here. And we're gonna go down here because that would give you a more stable alkene. Then you can also have an oxime. So with an oxime, you start with something called a hydroxylamine plus an aldehyde or ketone. And then same thing, you just copy and paste the NOH onto the carbonyl. And then you get an oxime.
Reaction, just like mix between two reactants and it's the product.
Yeah, it
Without
is
changing anything.
reversible. It is reversible, but yeah, that is the product. And I think I'll show you the mechanisms for all of these, but that's kind of a waste of time for the exam. The two mechanisms that do matter for the exam are the Wittig and the Horner-Wadsworth-Emmons. Those are the only two he's going to test you on.
Is that one not reversible?
It is, I just didn't draw it. All right, there's a few more. So to get hydrozones, we react an aldehyde or a ketone with this thing. You remember what this is called? So you react aldehyde or ketone with a hydrazine, and then you get a hydrozone. It's like basically the same react. It's hydrazone up here. Yeah, I just didn't space it out. I know, I'm so sorry. And then cyanohydrin, I don't think he cares, but I'll just draw it. So cyanohydrin, aldehyde or ketone, you give it HCN, and you just get a CN attached to it like this. What was it? To C triple bond to an N. And then there's two different kinds of reductions we can do on aldehydes and ketones. I think ketones. So you can have Wolff-Kishner, where you have a ketone and you react it with a hydrazine.
It's just ketone, right? Not aldehyde.
I don't think so. So when you react it with a hydrazine, you just get, well, the ketone turns into a CH2. You just cut it off. Oh, sorry, it's not just a hydrazine. It has to be over KOH. Because if you just gave it a hydrazine, it would turn into a hydrazone. So you need that base on the bottom to actually get rid of the ketone. And then Clemmensen reduction, same thing, you just chop off the ketone, but you use a zinc mercury amalgam over, what was it, HCl. So you have ZnHG on top, HCl on the bottom, same thing, you just cut off the ketone.
The Wolf-Kishner product, is that RR or R?
RR,
HCl,
yeah, ZnHG over HCl,
you can use any other acid also.
I think so.
That one, the KOH on the other one, can you use anything else?
I don't think you can. If you can, I've never seen it with anything else. Okay, so we finished the first part, the acetal stuff and the amine stuff. And we can start Wittig. So with Wittigs, you just turn an aldehyde or a ketone into an alkene. So the general reaction, it seems kind of intimidating because the mechanism is like gross and huge, but it's very simple. So you start with the carbonyl, and then you have this thing, which is called an ylide. So the ylide has that form, but it can also take this form. Because you see lone pair, and it can just hop down there and do resonance. So with an ylide, you're gonna have this P and then triphenyl phosphate thing on one side, and then this carbon with two R groups attached to it on the other side. All you need to do for Wittig is chop like the oxygen off of the carbonyl like this, and then chop the PPH3 off like that from the ylide. And then you just get rid of those two things, and then you mash the rest together, and then you get an alkene product. So you can see in this product, we have the original two R groups from the carbonyl, and then these two R groups from the phosphate ylide. And you get this your byproduct, but it's really that easy. So every time we see a PPH3 and some kind of carbonyl, that's exactly what we're gonna do.
What's the name?
Of this, oh, it's an ylide. Also called a phosphorane.
That's how it's spelled, why?
Yeah.